Good morning, everyone, from my side. Thank you for joining the session. I hope you are enjoying the conference so far, and let's talk about Python and OpenTelemetry. So I'm Christos. I'm a software engineer at Elastic, and I am mostly focusing on observability space over the past years. And over the past 2 years and a half now, I have been an OpenTelemetry contributor, where I am approver and code owner in various sub-projects of this ecosystem. And I am also a CNCF ambassador, where CNCF is the Cloud Native Computing Foundation. Let me ask you, how of you are familiar with CNCF? Okay. How of you are familiar with OpenTelemetry? Okay. And I guess you are familiar with Python, so I'm not going to ask this. But yeah, so CNCF is the Cloud Native Computing Foundation. It is an open source foundation that maintains projects like Kubernetes that you might know already. OpenTelemetry is another CNCF project. Then Argo CD, Prometheus, these sort of cloud native projects belong to CNCF. And OpenTelemetry specifically is about observability and is the second most active project in this foundation, right after Kubernetes, that you might know already. I think it's quite popular, so you might have seen this, but you don't remember this now. So if you are dealing with observability, this is something that you definitely need to check at some time, because it has very big momentum right now and is getting the standardized way out there to implement observability based on open source tools. So yeah, I will start with providing a definition of OpenTelemetry. And first of all, I like to think of OpenTelemetry as an open source observability framework. And specifically, it is a set of specifications and implementations for observability. Usually, we refer to it as OTEL. It is the acronym. So if I mention OTEL, it is OpenTelemetry. I'm not drunk. So yeah, with OpenTelemetry, you can do multiple things. For example, you can use the language-specific instrumentation libraries, for example, for Python, so as to instrument your applications and start collecting telemetry signals from them about how they are doing, their performance. Then you can use the OpenTelemetry protocol, also called OTLP, send them to another OpenTelemetry project, for example, the OpenTelemetry collector, which can run as a gateway, and it can receive, process, and export data to various observability backends like Prometheus, Jaeger, Elasticsearch, and so on. Now, the protocol provides support for observability signals like traces, metrics, logs, and profiles. We also have another project called Semantic Conventions, which tries to solve the most difficult problem out there in computer science, which is naming. So Semantic Conventions provide guidance on how to name variables and your telemetry in general. So whenever you want to refer to the name of your service, for example, you don't call it service_name. We have a standardized way to call it, and this is service.name. So you have consistency across your telemetry and your observability data. And another use case is to have the collector running on the edge, which means that you can collect data from infrastructure, systems, databases, and any other use case that you might have for your observability needs. Now the signal, the protocol is a protocol buffer schema definition, essentially. And this means that we have specific structs that we can use. And for example, if we want to describe a log, we have the log record, and this comes with specific fields like the severity text, the body, and so on, others that I skip here, that you can use to describe your logs. And additionally, you can have extra attributes which follow the semantic conventions, providing more context about your logs. And on the resource level, you can have resource attributes, as we call them, which provide information about the resources that emit this telemetry or are related to this telemetry. For example, the name of the host that you are collecting this telemetry or the name of the service that generates this log. So it is a protocol buffer schema definition implemented over gRPC and HTTP. Nothing really sophisticated. For Python specifically, there is a language-specific implementation, a library that you can use to instrument your applications and start collecting telemetry from them. And the project is organized with an API which provides the interface to generate telemetry data, and then an SDK which actually implements this interface. Now for the telemetry signals, OpenTelemetry for Python, the library is in a stable release for traces and metrics, but still in experimental for logs. But this doesn't mean that you cannot use logs already if you want. And you can find the link to understand more about the life cycle of stabilities. And now that we have a nice overview of what OpenTelemetry is, let's try to understand a little bit the signals, the observability signals, for those that are not familiar. I guess logs and metrics is more straightforward to understand. Maybe tracing is not that much. So let me ask you, who of you know about tracing? Who of you have collected traces? Okay, fine. So I like to think of traces as transactions, which means that while the application is executed, you start tracking the application execution so as to know the performance of this application. And a trace to me is like a transaction, which means that the whole execution, for a whole complete execution of your application, for a specific action like to get all the customers of your application, we have a single transaction, a single trace. And then for smaller execution blocks, we have the spans, and all these come with their IDs. So in this example here, we are the customer, we want to get the user, we want to get all the customers from the API service. So we start with a transaction, this comes with a trace ID, and then we start with a smaller block, the span, with its own different ID, and then the API service makes two different requests to another microservice, for example, a customer service or another service in general, and then we have two different spans. So we have three different spans with three different IDs, and all these share the same trace ID because they belong to the same trace, the same transaction. So we can build a dependency graph with all this information. We can track the execution of smaller execution blocks or for the whole transaction, and we can start getting nice insights of how our applications are doing. We can even draw a dependency graph and know how the microservices, for example, interact with each other. And this is also called, in distributed applications, distributed tracing. And I guess that's all about tracing in general. And in order to implement this in Python, we can use the OpenTelemetry library. In this very basic example here, we start a trace provider. We also attach some resource attributes to it so as to know the service that emits this telemetry. And then we build the telemetry pipeline, as we call it. So first we have the provider that generates the telemetry. Then we can have processors, for example, a batch processor, which can probably batch the spans or the traces if needed. And then finally in the pipeline, we have the exporters usually, which are used to export the data to another system or to the console or whenever you want to send them. In this example, I use the console exporter, which just sends the data to the console. And finally, the important part, I create a trace and a single span with the name foo. And inside this context, inside this span, I execute this very interesting thing, this hello world print message. And if I execute this, I will see in the console the hello world, and the exporter will send also the span in the console. And this is the first span that we can have. This is the first telemetry signal. This comes with a trace ID and the span ID, additional resource attributes, the service name, for example, I mentioned. We can find the start time, the end time. We can calculate the duration of this execution. So we can start building nice insights for the execution of this important application, the hello world. Now for logs is more or less similar. In this example, I have traces and logs in the same example. So for logs, I need to also start a log provider. Again, I need an exporter. In this example, I have an OTLP exporter, which means that I can send the data to an OTLP remote endpoint that can receive OpenTelemetry data. I use the provider, I register this with a handler, then I will do some logs. And the most important piece here is that I will generate a log, an error log, the very last one here on the bottom, and I will generate this as part of the specific context of the specific span, the foo span, and I want to see how these two different signals, the span and the log, can be correlated to each other. So on the left side, I have the span similarly to what I had before, with a span ID and a trace ID. And on the right side, I have the logs that are sent to an OpenTelemetry collector that can receive OpenTelemetry data. So it's another component, but this is not the important part here. And the log looks like this. So I have the body of the log, which indicates that we have a major problem. And here I can see that this telemetry has come with, is linked to the trace and the span that is actually related to this log, right? So I can start, for example, investigating this log and then link to the other signal, the trace and the span. And I can see, for example, what are the dependencies to this span and start investigating the problem more, and vice versa. I can start with a span if I identify that the execution time is very big, for example, and something seems problematic. I can jump to all the correlated logs and start investigating the messages there. And we call this in observability signal correlation, and something that is usually very useful. And last but not least, metrics. Again, we can generate metrics from our applications. We can use the OpenTelemetry library again to start a provider, and then define different types of metrics like counters, histograms, up-down counters. We can interact with these metrics. For example, in the demo later, we will have a counter which measures the recommendations that our service does, and we can calculate, for example, the rate of the recommendation service. So if this rate goes down, probably something is wrong, unless the traffic is actually down because users do not use the application. And this is more or less about instrumenting our applications, but you can notice that I need to change the source code. So I need to manually instrument applications, as we call it. It's called actually manual instrumentation. Yeah, and if I send these metrics to the collector and then to the console, the data look like this. Usually you need to send the metrics to a backend like Prometheus and start like visualizing the data or creating alerts and so on. And things can become more interesting if you use the auto instrumentation support that OpenTelemetry provides, which means that you don't need to change the source code a lot. And in this example, if you have a Flask API server, you can use the OpenTelemetry instrument wrapper, which is actually an agent that uses monkey patching to wrap the methods and the functions at runtime of known libraries and start generating telemetry from them without you having to change the implementation or whatever. And there is support for known libraries. So, for example, if you're using Flask or Django or other known libraries out there, this wrapper here can provide telemetry instrumentation out of the box without need for manual instrumentation. Usually you need a hybrid approach because you also need to instrument the parts that are not instrumented automatically. So to make this example more complete, here I have a client code. I manually have to instrument this. I have a client span. Then I create another span, which is the child of this span, just for the sake of the example. And then I will execute a request to the server. And yeah, we'll see what will be the output. Everything goes to the console in this example, and you can also find the examples online. Then, yeah, right. First, I have the client span. Then I have the child of this span, the client server span. You can see that I already have this relationship here because they share the IDs. The parent ID of this span is the span ID of the first one. And then I have the context propagation to the other side, to the server application, and this comes from the auto instrumentation part. And again, this is a child span of the previous one, and all these share the same trace ID. So I can see how already I can identify relationship and draw a service graph between these two different parts of the application. Right. So yeah, the important part here is that on the left side we have the manual instrumentation outcome, and on the right side you have the automatic instrumentation generating the telemetry automatically for us. Now, yeah, based on the first question, who is familiar with Kubernetes, I guess you are not running on Kubernetes your services. So yeah, anyone runs on Kubernetes? Very few people. Okay, that's fine. So Kubernetes is an orchestrator to run that you can use to run containers to deploy your applications. So auto instrumentation can become even more seamless on this example. If you're running on Kubernetes, you can have the OpenTelemetry operator, which is actually another application. It is a controller and can automatically identify applications that can be instrumented by watching the API server of the Kubernetes cluster, let's say. And it can mutate, can patch the specification of the application at runtime, and without you having to change the entry points of your containers, for example, or downloading all including the dependencies in your Docker images, for example, the operator will do this for you during the deployment time. How this will happen? You need to install the instrumentation resource on the cluster. It is something that the operator can understand and specifically enable the Python instrumentation. And then all the applications that we want to have them instrumented, we need to annotate them with a specific label, the instrumentation inject Python, set to true, and then using our images without changing the entry point or having dependencies included, we just deploy this on Kubernetes and the operator will do this for us automatically. So this provides a more seamless experience for users, and yeah. And another example from like real world, let's say deployments, is when you want to ensure the resilience of the log collection for your observability solutions. So, for example, if you have logs that contain crucial information that should always get collected, it might be risky to send them directly from the SDKs, from the instrumentation libraries, directly to an observability backend using the network, the OTLP protocol over the network. Because if the network goes down and the application crashes, then you won't have the chance to collect these logs. So in this example, in this case, you can consider writing the logs directly to files and then have another component to asynchronously collect these logs. And there is a nice blog post in the OpenTelemetry blog about this deployment strategy. And the thing here is that the instrumentation libraries are configured to write the logs to files, usually, as we know logging traditionally. You can use a specific format called OTLP JSON encoding, and then you can have the collector scraping these logs, extracting all the information, unmarshalling the OpenTelemetry data, doing, for example, further processing like adding additional metadata from the host or your containers, whatever, and then send the data to an observability platform. It's a very interesting use case. You can check the blog post. It's something that I've seen users being interested into this. And in order to achieve this, you need a specific exporter to translate the OpenTelemetry data from the library to the OTLP JSON format, and either write this to the console or write this to a specific file. Unfortunately for Python, there is no such exporter yet, so I had to implement this and experiment with this on my own. This is the source code. You can find this GitHub source, this gist here. And I also filed an upstream issue for the library, so maintainers have found this interesting, so probably this is something happening soon. The OTLP JSON format looks like this. So it's the OpenTelemetry data in a JSON format, and we have one log record per line, and then we can use the collector to parse this back, do additional processing, and so on. There are some specific components that you can use here if you're interested to check them. And now we will see how all these can work together with a demo. I will be using this OpenTelemetry demo, which is the official demo of OpenTelemetry. It is actually a web store that sells telescopes and related stuff, because OpenTelemetry's logo is a telescope, so that's the reason. And it is an application that consists of multiple microservices. All these are written in different languages. Only this small one, recommendation service, is written in Python, but we can work with it. It's fine. And I would highly recommend, if you want to check OpenTelemetry, to start with a demo. It's a nice way to deploy this locally using Docker Compose, or even running on local Kubernetes cluster. to get an idea and start with OpenTelemetry. I will be deploying the demo on Kubernetes and using the official Helm charts, which is a way to package Kubernetes stuff and deploy your applications on Kubernetes. You can check it if you want. And in the first part, I will be sending the data to Prometheus and Jaeger. These are CNCF related projects. They are completely open source. You can use them. You might know them already. And metrics will go to Prometheus and traces will go to Jaeger, and then I will be using Grafana to check the metrics and Jaeger UI to interact with the traces. How this is done, the SDKs are configured to send the data to a gateway, the OpenTelemetry collector, and the collector runs on the same cluster. It's a different application in a different container, and it is configured to send the data using OTLP to two different backends, the Jaeger backend and the Prometheus backend. And on the second part, I will bring down the demo and I will use a different backend. I will send all the data, all the signals to Elasticsearch, and I will check how I can search them through Kibana. In this case, I have all the signals in the same data store, so it's even more convenient because I can do signal correlation easier. And yeah, let's do this. Now it's the interesting part. So I have already installed the demo to save some time. So the command to use is this helm install command. When you will install the demo on Kubernetes, you will see this nice output here. Some instructions on what you need to do next. First of all, we need to, because I run this locally, you need to forward the port from the Kubernetes cluster, the containers, to your local machine. So as to interact with this, I've done this already. And here I have some links that I can use. For example, the web store, the Jaeger UI, Grafana, and so on. There are other pieces like load generator that you can use and feature flags, things that you can enable or disable different features to check them through the demo. And it is already running, so I will go and generate some telemetry, some traffic and telemetry. Does it work or? Okay, so I will go and buy some stuff to spend some money on this website. So what I want to achieve here is to produce recommendations. So I will be checking different products so as to get recommendations from the recommendation service. Let's buy something finally. All right. So now if I go to the Jaeger UI, I can find the system architecture here. I have the service graph. Here I can see how the recommendation service interacts with the other microservices. And I can check for the recommendation service and all the related transactions that I can find here. I can find the latest distribution. I can find how they are distributed in the timeline here. I can, for example, check this one, which seems heavy. And yeah, here I can see how the whole trace is organized, the complete transaction with the different spans. And this is the recommendation span, which comes with all the related logs, additional metadata like what is the deployment name, the service name, and so on. Now I will go to Grafana to check the metrics. This is the recommendation rate, and I think we're with time. Still going? Okay. Let's bring this down and try to do the final step, which is to send to Elasticsearch. So I'm using a different configuration here to send to Elasticsearch. I will need to forward the port again because the applications went down. Yeah, it takes some time. While it gets started, yeah, if you have questions, you can check the CNCF Slack. There are some channels that you can visit. Everything is open source. It is community driven, so you can even start like following the project. If you want to start contributing to open source, Python special interest group might be something that you need to check. You can check the GitHub projects and start like searching for some first issues that you can contribute. It's a really nice project there. And let's see. It seems that it runs. Let's see how the application, the microservices are doing. Everything is running. Cool. So I saved some time. So I will go to Elastic. I run on Elastic serverless. I send the data there. You can start with a free trial if you want to check everything without paying. And if I go to the service inventory, I will find all the services here. I have a service map as well, as similar to the one that we found before in the Jaeger UI. It's not really convenient to find this, but it is here. And let's drill down to the recommendation service. And here I can find a nice overview of the throughput and the latency for this service. I can find the spans or the transactions, as we call them. And I can drill down to this specific type of transaction, the list recommendations. And here I can find how it is the latency distribution for this type of traces. And here I have the trace samples. So I can find the metadata here. I can get all the logs that are related because I can correlate them using the trace ID. So I can jump from one signal to the other and start investigating the application more. And I can also check my metrics. Here is the recommendation. I guess that's all then. Thank you.
Thank you very much.